As demand in electrical consumption increases, there is a need to use alternative energy, mainly PV solar system, to fill the existing gap. Hi, welcome to the PZ Engineering channel, Passion to Excel. In this video, we are going to show how to design and simulate 33 megawatt peak grid-tied PV solar system in MATLAB Simulink software. Before we start our simulation, I would like to request, if you're not yet part of our family, please subscribe to our channel, share our content, comment and like this video. You can as well donate to our channel to have a specific models or a specific attention in your request or in a proposal for a project. You can as well join our membership team in order to have access to all the models and guidance in your project. Grid-tied system is a PV solar system connected to the power grid. The normal operation is PV solar system normally feeds with the grid system utility. PV solar system share the load with a grid utility. When the grid is off, the PV solar system does not supply. Grid-tied inverter measures the grid and only supplies when it senses there is a voltage at the grid side. We have our PV array, inverter, the load meter, and our grid utility. Here is our system parameters. You have Canadian 375 watt mono, total number of panels 88,000 panels, number of panels in parallel in series 22, and we have 4,000 strings. Rated in power, inverter power is 33, performance ratio is 83%, load demand 60 megawatt and grid 70 megawatt. Here you have our site layout. In the ground, PV array is the blue, the proposed substation location is the gray, the grid-tied inverters are the red ones, the existing 11 kVA line is here, and you have the pathway where they have 5 meters to walk around the plant. Now let's go to our MATLAB. This is our 33 megawatt peak plant in our MATLAB Simulink software. I will be introducing each component and the parameters of each component. All these parameters, you can get it from the library browser. Please don't forget to like the video, comment and suggest any topic that you can work on. In case if you want this model, you can contact us via email or donate in this video through a thanks button, and we'll send you the model. Now let's introduce each component. Now let's introduce each component. Here we have our PV array, here we have our grid-tied inverter. Here we have our 3-phase breaker and we have 3-phase measurement. Here we have our load demand and our grid. And scope our solar. Let's start with our solar irradiation. We have our solar irradiation. Start from 0 to 3, and from 3 to 5 it increase, and from 5 to the infinite it produces. Now have our temperature. You have our temperature. Now let's open our PV array. Our PV array, here we have our sub-arrays, 4 sub-array. Total number of panels we have our 22 in series and 1000 in parallel, which gives total to 22,000, which each sub array is 22,000 panels, and total is 88,000. We have our V system 39.8 times 22, and our V maximum 47.6 times 22. Now let's open each sub array or panels. We have these are our panels parameters: Canadian 375 watt, 22 in series, 1000 in parallel. The same applies to each sub array. I will just open each sub array to see the parameters. The same applies here. I'm just opening for you guys to see. Now let's go to our MPP control. We have our MPP control. Let's open our MPP control, which you can follow as it is and change according to your parameters. Control based on the perturb and observe algorithms, and we have our parameters. You can follow as it is. You can follow. And here have our unit delay. That's the value, that's the parameters. You have our boost average, boost converter average. Let's just open it. That's our boost. We can follow as it is. That's how we calculated. You can follow as it is. Here we have our, that's a capacitor, that's the value. And we go back. The same applies to the other MPPT. Here we have our VD, which is measuring the DC voltage. Now let's go to our grid tie inverter. We have this is our inverter, universal bridge, which you can get from library browser. Now you have our inverter control. I'll just go through it. Here we have our gain, the per unit. These are the value of our discrete three-phase PLL mask. And here we have our transformation, which you can get. And we have our transformation mask. The same is applied to this one. And here we have our selector 2. And we go back, we come to our VDC regulator, VDC reference, VDC nominal. Here I have our PI controller. And we go back to our current regulator. And we have our generation. Now we have our three-phase breaker. That means it's going to, the normal operation is open and we're going to switch from 3 to 8 seconds. We have our three-phase measurement. Here's to measure our PV, the AC output from our PV array, which we measure there. Here we have our grid. Our grid is 70 mega voltage ampere, MVA. This is the value. There is our three-phase 70 MVA, and then your 550. You have our three-phase measurement to measure the voltage produced by the grid or supplied by the grid. You have another three-phase breaker. The normal operation is open and will close from 0 seconds to 10 seconds. And here we have our measurement, and you have our to measure the power supplied by the grid. And from there we go to our load demand, which is being supplied by PV array and the grid at the same time. Here we have our load 60 megawatt, 60 megawatt. Then everything, all these components, you can get it from our library browser. You can research it, or as I say, if you want this model, you can as well donate to this video, and then you'll get access to our model. Now let's run our system. Please don't forget as well to subscribe to the channel, share our contents, comment, and like this video. Let's run our model and see the behavior of our system. Let's be patient, waiting. Now let's check our results. Here we can see we have our solar radiation, we have PV array power, we have our PV AC power, and you have our grid power. As you can see, from 0 to is not supplying, and then from 3 seconds the solar radiation comes out and the PV array starts supplying, and increase at 5 seconds. And here we have our AC. After it is the output of our inverter, which is supplied from 3 seconds to 8 seconds. And then we have our grid, which when the solar is supplying, the grid supply less. Thank you so much. Please don't forget to subscribe to the channel, share our contents, comment, and like this video.